So in this video, I'm going to be working with a turbine driven by flowing fluid, and I'll be using a kinetic energy and momentum balance to find the best ratio of outlet to inlet fluid velocity to get the maximum power generation out of this turbine. So to start the problem, I'm going to go ahead and just draw out the turbine and the scenario. So we have a turbine in the middle, and it's got blades. And I'm going to go ahead and define some terms for this turbine. So I'm going to define S, which is the cross-sectional area of the blades that the fluid is going to be flowing across. So we're going to have fluid coming in this side, and it's going to be at a velocity of V. And so we'll have S times V, and this gives us the volumetric flow rate of fluid moving through the turbine. Since we'll be working with momentum and kinetic energy balances, we want this in a mass flow rate. To get that, we just have to multiply by density. So that now I'm going to go ahead and define an area off to the left, and this will be called A1, and this is the area of fluid that is interacting with the turbine. So there's going to be fluid flowing this way towards the turbine. It's going to go in and spin the turbine. So again, it's going to have its own velocity and density. And this gives us the mass flow rate of the fluid that's entering the turbine. Then again, on the other side, once the fluid goes in, it's going to have to come out. And so I'm going to define another area, and this area is much larger. It's larger because as the fluid flows in and turns the turbine, it loses kinetic energy, so it comes out slower. So the mass flow rate of fluid coming out of the turbine can be represented as the density of the fluid times the cross-sectional area times the velocity at that position. So now from here, before we get started with driving the equations, I'm going to go ahead and define the ratio that we're looking for, which is R. And that is the ratio of V2 over V1. And so we want to find the value for R that gives us the most power generation. So I'm going to go ahead and start with a momentum balance. So what this looks like is the change in momentum of the system with respect to time is equal to the velocity going in times the mass flow rate going in minus the velocity going out times the mass flow rate going out of the system plus the force applied to the system. So from here, we're going to assume that we're at steady state to make the calculations a little simpler. So at steady state, all changes with respect to time are 0. And we also can define a uniform mass flow rate. And so I'm just going to define our mass flow rate as M, and this equals M in and M out. And we can also go ahead and define it using rho SV. Since the mass flow rate throughout this whole problem is the same, we can calculate the mass flow rate using rho times S times V. So from here, I'm going to go ahead and plug these values into our equation. So I'm going to move the force to the left-hand side. So we'll have negative F equals, well, our V1, or our velocity in is V1, minus our velocity out, which is V2, times our mass flow rate, which is rho SV. Now from here, we need to relate this to power. And so an expression that relates power to force is power equals force times velocity. But since we are interested in the force of the air on the blades, we need to make sure that this is negative, because the positive F, the positive force, represents the force of the blades on the air, but we're interested in the opposite. So we can go ahead and plug in our expression for negative F now to the power equation. So we'll have V1 minus V2 times rho S, and then we'll have V squared because there's V in both of these expressions. And this is our first power equation. So from here, I'm going to go ahead and write this off to the side, and we'll use it later, and we're going to use a kinetic energy balance to define another power equation. All right, so from here, we can use a kinetic energy balance to get a second expression for the power. And so what this looks like is we can take the change in kinetic energy and divide it by the mass, so the change in kinetic energy on a per mass basis, and if we multiply it by our mass flow rate, that gives us the units of power. So we'll have joules for kinetic energy divided by kilograms multiplied by kilograms per second, and so the units of power is joules per second, so these units check out. So from here, we just have to again substitute our values from the problem into this. So kinetic energy is just 1/2 mv squared. Well, we're dividing by m, so we're just going to have 1/2 times the velocity squared. So what this looks like is we're going to have the velocity at position 1 going in squared minus the velocity going out squared divided by 2. This m cancels out, and then we have to again plug in our mass flow rate, which is rho s v. So now from here, I'm going to kind of get rid of this expression and copy this power expression off to the side, because I'll use it again later. And our next step in this derivation is to set these two power equations equal to each other. So our second equation, we'll set it equal to V1 minus V2 times rho S V squared. So right away, we can go ahead and cancel out S and rho from both sides. We have a V and a V squared, so we can cancel those out. And now I'm going to go ahead and solve this equation for V. Because right now we have V1 and V2 defined as the velocity going in and the velocity going out. But this velocity at the fan is still kind of arbitrary, so we can actually use V1 and V2 to get an expression for that. So go ahead and solve for that. We have V on the left-hand side of the equation. And so we just have V1 minus V2 over 2. And then I just need to divide over V1 minus V2. Now from here, we can go ahead and simplify this a little bit more. I just need some more room on the whiteboard. And so if I go ahead and expand the numerator in this expression, it gives me V1 minus V2 times V1 plus V2. And then we have 2 times V1 minus V2 in the denominator. So these two terms cancel. So now we have the expression for V is just the average of the inlet and outlet velocity. So now that we have that expression, we can go ahead and substitute it back into one of our two power equations. So I'm going to go ahead and use this one because it'll be a little simpler. So what that looks like is we have V1 squared minus V2 squared over 2 times rho S, and then our new expression for V, which is V1 plus V2 over 2. Now from here, I'm going to go ahead and pull out the constants. So rho S and the 2's in the denominator, out of the frame. And then I'm going to multiply out our velocity terms. So what this looks like is rho times S over 4. And we have V1 squared times V1 gives V1 cubed. V1 squared times V2 is just V1 squared times V2. Then we have negative V2 squared times V1 and negative V2 squared times V2, which is just V2 cubed. So now from here, I'm going to go ahead and factor out a V1 cubed term, and that'll actually allow us to implement in our ratio, and we'll be able to solve for the maximum power. So just do it at the bottom. So I factored out a V1 cubed. So in our expression, we just have 1 plus, this is V1 squared divided by V1 cubed. So we're left with V2 over V1 minus, we have V2 times V1. Once we divide it over, we have V2 over V1, and these are both squared. And then for the last term, it's just V2 cubed over V1 cubed. And so now if you notice in this bottom expression, we have V2 over V1 3 different times. And so we can go ahead and substitute R in this expression. So we have the power equals rho S times V1 cubed over 4 times 1 plus R minus R squared minus R cubed. So from here, we want to get at the maximum power. So in order to do that, we need to take the derivative of power with respect to R. So these derivatives are relatively simple. So derivative of 1 is just 0. Derivative of R is just 1. Derivative of R squared is just 2R. And the derivative of R cubed is 3R squared. So from here, since we're looking at the maximum, we can go ahead and set this equal to 0 and solve it like a regular quadratic. So to do that, I'm just going to go ahead and factor it out. So we're going to have 1 minus 3R and 1 plus R. Well, the value for the ratio R has to be in between 0 and 1. And so if we solve this solution, it'll give us a negative number, so that's clearly not the solution to our problem. So if we go ahead and solve this left side, we get 1 over 3 equals R. And so what this tells us is no matter the specifications of the turbine, doesn't matter how many blades, how big the blades are, as long as the ratio of the outlet velocity over the ratio of the inlet velocity is 1 over 3, then the turbine will be able to create maximum power.